Welcome to a tutorial on low-pass active filters. Okay, so when it comes to low-pass filters, let's just get on to a low-pass filter first. So whenever we're just talking about a low-pass filter, we know that, well, using passive components at least, a low-pass filter would appear to look something like this. Okay, so I'm just gonna complete this circuit diagram over here. There you go. So we'd have a resistance, okay, I mean a resistor, sorry, and a capacitor, well, configured joined together somewhat this way, and you ground this terminal and apply the input right at this end of this resistor. Okay, so whenever you have this kind of a circuit with an input signal applied over here, which is of course a sinusoidal signal, okay, then whatever you get is a passive low-pass filter. Okay, so this is basically a passive low-pass filter. Okay, so I'm just going to write that down. Now, what happens over here is that, well, in this particular passive circuit, I mean, why do we call it passive? It's because we're using passive components over here, like resistors, capacitors. Okay. Now, whenever we're talking about the term active filters, okay, so whenever we are talking about active filters, now what does this term active mean? Okay, so you see, active filters are also certain filter circuit, like let's say for example this passive filter that we have over here, we know that it's a low pass filter, meaning it would have a frequency characteristic, I mean output characteristic. If we just plot the output voltage versus frequency over here, then of course it's going to have an output frequency characteristic that's going to look something like this. Okay, so here obviously we're going to have some sort of a cutoff frequency. Let's say this is our cutoff frequency termed as FH, and so what this circuit basically does, it just lets the frequencies below that of the upper cutoff frequency, that is FH, to appear at its output, okay, as the output voltage. So those frequency signals which just lie below that of its upper cutoff frequency are passed on to its output unattenuated, while those above FH are attenuated by the circuit itself, as we described in the previous tutorial. But whenever we're talking about active filters, on the other hand, then we should always keep in mind that active filters basically consist of two parts. One is of course a passive filter. Okay, so one is of course a passive filter circuit. Okay, I'm just gonna write that down over here. And the other is an amplifying device. Okay, there you go. So other is an amplifier. So the devices that can basically function as an amplifying device or an amplifier are basically BJTs. Okay, then you can have FETs, and also you can have op-amps. Okay, so that's operational amplifiers. So these kind of devices are used in an active filter circuit to function as an amplifier, while we have a passive filter circuit over there that basically does the filtering. So whenever you combine both of them into a particular circuit, then you have an active filter, right? So since we're going to discuss low-pass active filters over here, so then let's just get on to this circuit that we want to discuss about. Okay, so now you're seeing an op-amp, right? And we're going to use the op-amp as the amplifying device for our active low-pass filter circuit. Okay? And for that reason, we're just going to make a non-inverting amplifier out of this particular op-amp, right? Right, so here we have a non-inverting amplifier configured out of this op-amp. Okay, so as you can see, we've connected the resistors. Okay, this is the feedback resistor RF, and this is the non-inverting input resistor. Let's just call it, this is the inverting input resistor. Let's call it R1. Okay, and here we're going to provide the input to the positive input of this particular op-amp. So let's just call that V1 over here. And from our previous experiences about the op-amp circuits and all, we know that the gain of this particular amplifier circuit is given by, let's just call it AF, would be given by 1 plus that of RF by R1. Okay, so this would be the gain of this particular op-amp circuit. Now, as I said, we need an amplifier and also a passive filter. And there's our passive filter circuit. So what we now need to do is we just need to join them. Join the passive filter's output terminal, okay, to the the non-inverting amplifier's positive input terminal. Okay, so let's just join it. There you go. So this particular circuit becomes our active low-pass filter, okay, using an op-amp as the amplifying device. So here, if we would apply, or rather if we would just connect some sort of, let's say if we would just connect a sinusoidal source over here, okay, if we would just connect a sinusoidal source, any sort of AC signal, okay, that's serving as the input. Let's just call it VI instead. Okay, so when the frequency of this particular sinusoidal source would just be varied experimentally, we'll find that this particular circuit would just yield a characteristic somewhat similar to this particular characteristic that I've just given as a rough sketch over here. Okay, so as I said, the gain of the the non-inverting amplifier over here would be just given by this particular expression. All right, while the upper cutoff frequency, let's just call that FH. Okay, we'll be just referring to the upper cutoff frequency using FH. Okay, so this will be basically equal to 1 by 2 pi R2 C2. Okay, so that's the upper cutoff frequency of this particular passive filter circuit. Okay, so this particular thing basically means that below this frequency, all those voltage signals whose frequency just comes below the upper cutoff frequency would be just passed off to the output to appear as the output voltage unattenuated, and then those above it would be just attenuated by the entire circuit itself. So this particular circuit functions in a way that whichever frequency signals, if the input signals having frequency components that are basically lower compared to that of the upper cutoff frequency, whenever those those electrical signals, input signals, they just come over here at the passive filter's input, it just lets them pass to the input of the non-inverting amplifier. Okay, and the non-inverting amplifier would just amplify them, providing a gain of AF times to make them appear at its output as its output voltage. But if those input signals having frequencies greater than that of the upper cutoff frequency of this passive filter appears at the input, obviously they would be attenuated by the filter, and they would just appear as a very low magnitude output voltages at the output of this particular op-amp, okay, or the non-inverting amplifier, as they would not get a gain of AF times. They would not be amplified so large by this particular amplifier circuit. Okay, so those signals would be just attenuated. So these particular signals of having frequencies greater than the upper cutoff frequency would be just attenuated. Okay, and such frequencies that would be lower than the upper cutoff frequency would just appear as output. Okay, they would just be amplified. Okay, so that's the basic operation of this particular circuit. Now here, if we just try to numerically, or rather mathematically, treat this particular circuit, then over here we can see that the output of the passive filter is basically the input to this non-inverting amplifier stage. So here the output of this passive filter is basically taken as V1. Okay, so if we just do that, then by applying simple laws of algebra and considering the circuit theory, we can get, well, V1 equal to V in, okay, that's VI, all right, divided by that of 1 plus 2 pi, okay, or rather J of 2 pi F RC, right? So we're going to get this particular expression as the output from this, as the magnitude of the output voltage from this particular passive filter, where the impedance, okay, of the passive filter would be just given by R plus that of jxc, or rather, if I just write it down over here, it'll be just taken as, oops, a little bit of mistake over here. If we would basically take the impedance of this circuit, it would just come to R minus that of jxc, okay, not plus, right? So whenever we do that, then we're going to get an expression of R minus j divided by that of 2 pi f c, okay? That is j divided by that of omega c. So if we would just use this particular impedance expression, okay, and apply basic laws of circuit theory and take the output voltage across that of the capacitor, then we would basically be landing up with this particular expression that we have over here. Okay, now this is going to be the output from this particular passive filter, and now since this output of the passive filter serves as the input to the non-inverting amplifier, so this basically means that this signal is going to be amplified AF times. Okay, so here we know that AF basically is equal to 1 by that of 1 plus that of RF divided by R1. Okay, so this basically means here AF would just stand for the output voltage obtained from the amplifier itself, that is this particular variable, divided by, and that's going to be divided by the input voltage given to the amplifier, that is V1. Okay, that's over here. So this is basically, AF is basically equal to the ratio of VO by that of V1. So this particular thing actually implies that the output voltage VO would be, the gain times, that is 1 plus that of RF by R1 times multiplied to that of the input voltage supplied to the non-inverting amplifier, right? So in this case, if we would just put the expression of V1 that we obtained over here, then we're going to get the output of this circuit as equal to 1 plus that of RF by R1, okay, and it's going to be multiplied with that of VI divided by, let's take a look at this expression. Okay, we're going to get 1 plus J times 2 pi f R C. Okay, now if we would just put AF instead of 1 plus RF by R1, so that's kind of big, so we just shortening the expression a bit, so then we're going to be landing up with an expression of AF, okay, and divided by that, let's pull the page down a bit, 1 plus J times F by FH. Okay, so if we would just simplify this particular expression a bit, then we're going to get, or rather land up with this sort of expression. Now here in this expression, RC is actually, well, R2C2, right? So you know that here FH is equals to 1 by 2 pi R2C2. Then this actually means that, well, 2 pi R2C2 is actually equal to 1 by FH. So we've just substituted 2 pi R2C2 with 1 by FH over here. So that's why we landed up with this particular expression. So this is equal to the output obtained from this entire circuit over here. Okay, so we're getting the output from this entire circuit over here, and we've just calculated it using basic circuit theory. So that's what we're going to get over here. Now you see, this is basically a complex quantity, so if we would just take the modulus of this particular thing over here. Oh, and I just forgot to include VI. Okay, so that's VI. So if we just bring VI over here, that's VO by VI. That's the total overall gain of this particular filter circuit. Okay, that's we're going to get over here. So that is just given by AF by that of 1 plus J times F by FH. Okay, so if we would just take the modulus over here, since it's a complex quantity, then we're going to land up with this sort of expression. Okay, that's mod AV is going to be equal to the modulus of VO by VI. It can also be expressed in this way. Then we're going to get, well, AF by that of root over 1 plus F by FH whole squared. This is what we're going to get. Okay, so this is going to be the expression of the overall gain of this particular circuit, okay, the active low-pass filter circuit. Right, now this particular filter circuit is basically a first order filter, okay, so this is basically a first order filter, right? And why is it a first order filter? Because first of all, it consists of a single filtering, single passive filter stage applied to the active amplifier, the non-inverting amplifier's input, okay, so it just consists of a single filter stage applied to the amplifier input. That's why we just call it a first order filter. And apart from that, when we look at its characteristic, okay, its characteristics can appear somewhat this way. So if we would just plot the gain of the filter, that is AV, that's the overall gain of this particular active filter circuit, okay, versus that of frequency. Alright, then we can basically get a curve. We'll basically get a curve that would look somewhat like this. Okay, it'll have a roll off. Right, so here if I just extend the x-axis a little bit more, then you can see that over here somewhere at this particular point there is going to be the upper cutoff frequency, that is FH. Okay, so here those frequencies that lie below FH falls in the pass band of this particular filter circuit. So here we have the pass band, okay, ranging from the lowest frequency, that is from 0 to that of FH. So this is actually the pass band of this particular active filter, and there are those frequencies that lie above that of FH, okay, they just fall in the stop band, and this particular thing just goes on. So here we have the stop band of this particular filter circuit. Okay, so whenever we just do it, the frequency, whenever we just construct it, the frequency response should look somewhat like this. Now you can see here that the gain would be, if the gain is just plotted in the decibel scale, okay, then of course I should tell you that the overall gain of this particular circuit would be equal to that of AF. Okay, so the maximum gain of this particular circuit, that is AV max, would be just equal to that of AF for those frequencies that fall within the pass band of this particular filter. So here that's the maximum gain mark, okay, AF. And here at FH the gain just falls down to, I'll just point it out over here, root 2 times, 1 by root 2 times its maximum value. So here the gain, the gain of the signals at FH is equals to AF divided by that of root 2. Okay, so there you go. And now if we look at the curve over here, you can see that near FH, okay, that's the upper cutoff frequency, the curve just rolls off, okay, it just develops, or rather it just dips down. So this dipping down, okay, so this dipping down tendency of the curve is just referred to as a roll off. Okay, so this entire region is just referred to as the roll off of this particular curve. And well, the roll off just takes place at a certain rate defined by the roll off rate, okay, of this particular curve. So the roll off rate of this particular curve is about minus 20 decibels per decade. Now what does this thing mean? As I said, if we just plot the gain of this particular curve, of this particular filter circuit in the decibel scale, then this means that the gain of the circuit reduces by 20 decibels for every 10 times increase in frequency. Okay, so whenever the frequency increases by 10 times, the gain of this particular filter circuit rolls off or reduces by 20 decibels. Okay, so that's why you have a minus sign over here. So this is just defined as a roll-off rate. That's the rate of gain reduction versus frequency. Okay, so that's how it's just basically defined. Now it should be always kept in mind that for first order filters, okay, for first order low pass filters, I'll just write LPF in short, we always have the roll-off rate at minus 20 decibels per decade. So the curve just, the frequency response always has a roll-off rate equal to that of minus 20 decibels per decade. Okay, so this is a very important characteristics, what basically defines first order low pass filters. Alright, so That is also one of the reasons why we just call this circuit as a first order active low pass filter. Okay, now if we use the same first order active low pass filter circuit just with another resistor capacitor stage at the input, okay, so if I'm just drawing it somewhat this way, alright, so if we have one more capacitor over here, so then we get another resistor capacitor stage, that's an RC stage, and apply the input voltage from the sinusoidal source right over here, okay, and then join these two together. And instead of connecting this particular capacitor to ground, we just take it and connect it to the output of this particular non-inverting amplifier. So here, if we just call it if we just call this resistor as R3 and this is C3, then the resulting circuit that we get over here is basically a second order low pass filter. I'll just write LPF in short. So this is basically a second order active low pass filter. So there you go. So for this particular circuit, although the gain provided by the amplifier is just the same as before, that is AF, which is equals to 1 plus RF by that of R1, okay, although this remains same, but the upper cutoff frequency expression changes by a little bit. It becomes 1 divided by that of 2 pi, okay, R2 R3 and C2 C3. So that's how the frequency expression, the upper cutoff frequency expression basically changes. And so does the expression for the overall gain of this circuit, which is basically defined as AV. If we just take it as AV mod in this case, that's the modulus value, then we're going to get it as AF, okay, that's the gain of the non-inverting amplifier divided by that of root over 1 plus that of F by FH, this time whole to the power 4. Okay, so you can see that the power of this particular expression raises, just increases by 2 times, right? So this is how the expression changes a bit, and its frequency response characteristic would have a roll-off rate. Okay, I'm just gonna write down over here. It'll basically have a roll-off rate of about minus 40 decibels, okay, per decade, which is double to that of the first order filter. Okay, so if I just draw the graph, and here you can see the frequency response of the second order low pass filter, the one marked in red. Okay, so you can see that its slope is much steeper with a roll-off rate of minus 40 decibels per decade, okay, if the gain is plotted in decibel scale. And over here, as a comparison, for comparison, we've just traced out the slope or the roll-off nature of that of a first order low pass filter, whose roll-off rate is minus 20 decibels per decade. So they just kept side by side for comparison. Okay, so with that said, we just come to the end of this tutorial video. Hope you've liked our tutorial and we've been able to summarize all the necessary points. So we'll be seeing you in the next tutorial. So till then, it's just going to be a short goodbye for now, and thanks for watching.